Calorimetry Examples. In this video, we apply theory to a number of problems. Here is an example of calorimetry for two objects. 300 milliliters of water at 70 degrees centigrade is poured into a 120 gram aluminium cup at 20 degrees centigrade. Find the final common temperature TF, so we know they both have a final common temperature. The water is object 1. Its mass, M1, is 300 grams, and its specific heat is 4190 joules per kilogram per degree centigrade. Its initial temperature, T1I, is 70 degrees. The second object, M2, of 120 grams, is the aluminium cup, and its specific heat is 910 joules per kilogram per centigrade. Its initial temperature, T2I, is 20 degrees. We assume that the water reduces in temperature and the aluminium cup increases in temperature, and they arrive at a common temperature, so there are just these two heats, and we add them. Q1 plus Q2 equals 0. Q1 is M1C1 delta T1, and Q2 is M2C2 delta T2, and they add to 0. Note that the change in temperature is going to be positive if the temperature increases and negative if the temperature decreases. So there's going to be a positive quantity and a negative quantity adding together to make 0. So the change in temperature is final minus initial for both object 1 and object 2. And we have an equation, and we then solve for the final temperature TF, which turns out to be 66.0 degrees centigrade. Now we have an example of a more complex process in which ice is transformed to water and then can be regarded as a different object. So the problem is 70 grams of ice at 0 degrees centigrade are added to a glass of 350 milliliters of water at 25 degrees centigrade. Find the final temperature of the water. The ice is at 0 degrees centigrade, so it doesn't heat up, it just immediately starts melting. So first of all, Q1 is the amount of heat added to the ice to melt it completely. That is mass of ice times the heat of fusion, which is 23.38 kilojoules. Now we have a body of water at 0 degrees centigrade mixed with another body of water at 25 degrees centigrade, and we regard them as two different objects that exchange heat such that they both change their temperatures to the final common temperature. Q2 is the heat added to the mass of ice, which is now in the form of water, and its temperature increases, and so we need the specific heat of water to find Q2. The other body of water, the original 350 milliliters of water at 25 degrees centigrade, is treated as a separate object, and so we calculate the heat Q3 that is added to the water in order for it to reduce its temperature, and that is equal to the mass of water times the specific heat of water times the temperature change. So now we have three quantities of heat. We add them together. We see that in fact Q1 is a gain of energy by the ice in order to melt it. Q2 is another gain of energy by the now melted ice, so it's water at 0 degrees in order to heat it up. And Q3 is a loss of energy by the original glass of water. Solving this equation for T final, we find that it is 7.5 degrees centigrade. Here is a fairly complicated example in which we need to check phase changes to see what is realistic. A copper pot with a lid has a mass MCU of 2 kilograms, and its initial temperature is 150 degrees centigrade. We then take 100 grams of water at an initial temperature of 25 degrees centigrade and pour it into a pot, and the lid is closed. Assume that no heat or water is lost from the system. Find the final temperature TF and the phase of the water. There are three possible outcomes that we need to investigate. First, that the water just heats up to a final temperature that's below 100 degrees centigrade, so none of it converts to vapor, and it is liquid water, just hotter liquid water. The second option is that it ends up as a mixture of liquid and vapor at 100 degrees centigrade. The third option is that all of the water is converted to vapor and that the temperature of that steam is greater than 100 degrees centigrade. So we must test each option. In the first option, heat is added to the water and heat is added to the copper. There's no phase change, so these are the only two quantities of heat that are involved, and we add them together to equal 0. And so we see that each consists of factors mass times specific heat times a temperature change, as we've seen in a previous example. And solving for the final temperature, we find that it is 106 degrees centigrade. Now that is wrong because we started by assuming that the temperature would be below 100 degrees centigrade. So the fact that we get a temperature greater than 100 degrees centigrade means that our assumptions were wrong. So we can exclude this option. That means that at least some, or perhaps all of the water is converted to steam. In the second option, we have a final mixture of water and steam at 100 degrees centigrade. So what happens is that some of the water stays as water, and some of it is converted to steam. First of all the water must be raised by 75 degrees. Then a fraction x of the water is converted to steam, so that's a partial phase change. The third part is the heat added to the copper pot. We add all those to 0, and then this time we solve for x, and we find that it's 0.034. This is logically consistent because it is perfectly possible that 3.4 grams of water is converted to steam, and now we have a mixture of water and steam at 100 degrees centigrade. But let's check the third option, in which all the water is converted to steam. In this case, heat is added to the water to raise it to 100 degrees centigrade. Then an amount MWLV is added to convert all of the water to steam, not just some of it. Then the steam needs heat added to it to raise it to the final temperature, and heat is added to the copper. Solving for this equation, we find a final temperature of minus 122 degrees centigrade. This is impossible. It contradicts the assumption that the final temperature is above 100 degrees centigrade, so we see that this option is excluded. Therefore, it is option 2 that is the correct option.